universe. And then so Albert Einstein basically came up with his general theory of relativity, which basically talked about space and time being one entity and not different. So we basically talk about a four-dimensional space-time continuum. And then it also talked about gravity, where the gravity is not really a force, but it is an inherent property of the space-time itself, wherein it is brought about by existence of mass and of course energy density. So so in okay so according to his general theory of relativity, Einstein gave a set of 10 field equations, which are uh, which are given in this form, where these notations are basically to denote tensors. We'll not get into that for now. So in 1922, Alexander Friedman, he basically derived his own equations, which are known as the Friedman equations, which are given by these two. So here your A is the scale factor of the universe. The scale factor meaning by how much the universe is actually expanding. So you can understand, yeah, you can understand the scale factor through this. Now if you look at the first image, you can see that the sides are basically increased by a factor of 2 here, and the whole area is increased by a factor of 4. So for this particular region, your scale factor would be 4. So yeah, so that is about the scale factor. Now your A dot is basically at what rate the scale factor is changing. Okay, and here rho is the energy density of the universe. Energy density is basically how much energy you can put in a certain volume of space. And k is the spatial curvature. Spatial curvature meaning the universe could be positively curved, or in a sense closed, or negatively curved, or in a sense open, and it could be flat. So we talk about the curvature in terms of k. And this symbol here is lambda. It's basically the cosmological constant that was introduced by Einstein in his field equations. Okay, so here the second equation we have a double dot. So a double dot basically gives the acceleration of the universe. Now, why do we think the universe is accelerating? That was actually given, experimentally verified. So in 1927, Georges Lemaitre, he derived an expression uh, which related the velocity of galaxies which were receding away from us to the distance from us. So it was actually given by this equation here, which is the Hubble-Lemaitre law. V equals h naught d, where v is the velocity of the galaxies that are moving away from us, and d is the distance of separation, and h naught is the Hubble's constant. Now, this Hubble's constant is given by 74 kilometers per second per megaparsec. You could understand it uh, in this way. So the universe is basically expanding 74 kilometers per second faster with every increasing megaparsec distance. So again, this shows that the universe is expanding. Okay, so coming back to this. Now, if we put a dot equals 0 here, okay, I'm sorry. Yeah. So just consider the first equation. We can actually neglect these two terms, the one with k and the one with lambda. And if we only consider the first term and then put a dot equals 0, then we see that rho becomes 0 because 8 pi g by 3 is a constant. Now, what this means is that if the scale factor, I'm sorry, if the rate of the scale factor changing is 0, then you cannot have an energy density in the universe, which in other words could be written as, if I put some energy density in the universe, then the universe has to be either expanding or contracting. It cannot be static. So this was basically the foundation for the Big Bang theory. And as technology progressed, scientists were able to plot the scale factor of the universe, how it has changed from billions of years ago until now. And then this is the graph that they obtained. So you can see that until a certain point from the beginning, the scale factor is coming down, which means that the universe is decelerating, and after one point, the universe is accelerating. Uh, Now in this talk, we will not go into this part. We just focus on this part, the first uh, the first half of this graph. Okay, so now if we can zoom in, sorry, if we can zoom in into this point of origin, we find that the scale factor is extremely small. So at some point in the beginning of the universe, the scale factor was extremely small, which meant that if we consider any two distant points in the present universe, then they must have been extremely close back then. So, which uh, which leads us to the fact that the universe must have been in a hot, dense state, where the energy density and the temperature were much higher because of the compressed space time, because we had so much amount of matter being put into a into a very small volume. So that temperature, it comes up to more than 10 to the power 26 Kelvin. Now, initially, so in that plasma state, we had only elementary particles like your electrons and quarks, which were moving around due to the high temperature, and the photons that existed during that time, they weren't able to travel long distances because of the collisions with these elementary particles. Now, uh, so as the universe expanded and cooled, the temperatures dropped, and then and at some certain point, the temperature was just enough for the formation of neutral atoms. So your electrons combine with your protons and neutrons to form atoms. Now, as the universe expanded, there was an increased volume in the universe, and which allowed the light to actually travel long distances without interacting with any of the particles. Now, this light was detected. This Yeah, the same light that left the universe about 4 lakh years ago was detected in 19 somewhere in the early 1960s by two radio astronomers when they found a mysterious signal humming across the sky, so which was completely uniform. So this signal was later discovered to be the cosmic microwave background radiation, which when mapped, basically shows us a picture of the early universe. Now the CMB will be spoken about in the later half of this talk, so I'll not get into that. uh, okay, so Big Bang theory as a whole was an extremely uh, uh, what I would call a very plausible it could give a plausible explanation for all of the events that we know have happened in the universe. But there were certain problems or certain discrepancies which we encountered, which couldn't be solved. So in 1981, I believe, Alan Guth, he came up with the inflation theory in order to solve two specific problems, which were the horizon problem and the flatness problem. Now, the inflationary theory, it talks about a period of rapid expansion uh, much before the hot Big Bang phase. So the time interval that I'm talking about is a fraction of a second. So all this happening within 1 second. So as you can see, it expanded the universe by a factor of at least 10 to the power 26 within that time interval of 10 to the power minus 36 seconds to 10 to the power minus 32 seconds. So you can imagine the extremes that we're talking about here. So this time interval is basically known as the inflationary epoch. Now, how do we understand this inflation ho- inflation concept? So now, when so let's go back to the Friedman's equations. So when we look into the second equation, uh, if I need the acceleration to be positive, then I need the term in the bracket to be negative, because you have a negative here. A negative multiplied by negative will give you positive. So your rho plus 3p by c square should be negative. Now, so in cosmology, we usually put the speed of light equal to 1. So let's just do that. And what we get is rho plus 3p less than 0, which means that the pressure is negative. Now, you cannot have a negative energy density in the universe, so which means that a negative pressure component should have been present in order to inflate the universe. And this negative pressure can be talked about as the characteristic of a scalar field, which we now call as the inflaton field. Okay, now for the inflation theory to be successful, it needs to it needs to be able to inflate the universe. The inflaton field, it has to be able to inflate the universe along with along with satisfying whatever the Big Bang theory states. So when we talk about the inflation happening before the hot Big Bang phase, it should at some point stop, and then it should lead into the Big Bang phase. So these are the conditions that need to be satisfied. The first one is that a negative pressure substance should fill the universe, and then this period should be transient. So what transient means is that it should be momentary, and it should end after a certain period of time. Now, once it ends, it has to decay, and the universe has to transit from an exponential expansion of that 10 to the power 26 in that fraction into your normal decelerated expansion that was predicted by the Big Bang theory through this graph. Okay, so and then the most important point is that this decay must provide energy for the formation of your standard model particles, your electrons, quarks, and all of your muons and all of your standard model particles. So this process is called the reheating. Now, the Big Bang model talks about elementary particles being present in the hot Big Bang, hot plasma phase. So this formation of elementary particles should be directly followed by the uh, yeah yeah so this formation of the elementary particles should be directly followed by the experimentally verified Big Bang plasma phase. So this graph is usually this diagram is usually used to represent the evolution. So as you can see, this region of bright light is the inflation. It was extremely it happened for an extremely in a short period of time, and then after a certain point, the inflation ended, the scale factor reduced, and the expansion in a rate reduced, and after this it has been decelerating, and after a certain point it starts accelerating once again, and that is due to something known as the dark energy, which we won't be getting into in this talk. Okay, so I'll just give a brief idea of how the inflation actually took place. So we have the inflaton field here, and this is basically the potential representation. uh, Okay, so the inflaton field has a certain pressure, which is given by this equation. Your half phi dot squared is your kinetic energy, and V phi is the potential energy. Now, initially previously we saw that we need negative pressure for inflation. So which means that this entity has to be negative, and again transferring the V phi to that side, we get velocity squared to be less than the potential. So this is the necessary condition for inflation to take place. Now coming back to this graph, we can see that the field rolls down slowly here. Now the curve here is extremely it is not steep. So the potential is much higher than the velocity. So the inflation takes place until a certain point when the graph becomes steep. Now, as the graph becomes steep, the velocity increases rapidly, and when it violates that particular condition of the velocity being lesser than the potential, at this point, at phi n precisely, the inflation stops. Now, as soon as the inflation stops, the graph drops, and here this region is the reheating region wherein your standard model particles are found. Right. So once this is done, the this exponential expansion, what we saw, it drastically reduces, and then we get the normal, decelerated expansion that was predicted by the Big Bang model. So right, yeah. So I think that's it from my side. The problems that the Big Bang theory brought about, and the solution provided by the inflation theory will be given by my fellow teammates. I think Julie, you can take over. Thank you.
Okay, 1 minute. Can I share my screen? Is it visible?
Yes, yeah, it is.
All right, so the Big Bang model had two major problems. Those were the horizon problem and the flatness problem. I'll be explaining the horizon problem and how inflation theory solves it. So, in a nutshell, the horizon problem is the inability of the Big Bang model to explain the extreme uniformity or homogeneity that we see in the universe. So if you look at this image, this is a simulated image of the large scale structure of the universe. So each of these points that you see are galaxies or even clusters. These slightly yellow points, those are like clusters of galaxies. So we are looking at extremely large scales, like much, much greater than 100 megaparsecs or so. And as you can see, it's more or less uniform. And this it's not easy to explain this with the Big Bang, because now if you take 2 points on this image, they are separated by such large distances that light would have to travel for billions of years, and even longer than the age of the universe itself. And why is this traveling time important? Because for any 2 points to reach equilibrium or uniformity, it needs some time to interact, exchange energy, and kind of become uniform. We see this in, like, for example, um, uh, in diffusion. If you mix two different colors together, you need to allow it to mix for some time before it can become a uniform, single color. So what we are seeing in the universe is a uniformity across extremely large scales, which would have taken lots and lots of time to reach that kind of uniformity. So how is that possible? Let's look into it some more. So before we go into that, first let's kind of understand the concept of horizons. Yeah. So in in cosmology, the horizon size is given by this equation. It's integral CDT by AT multiplied by the scale factor AT. And the quantity within this integral is basically the size of what one would call like the co-moving distance, or the size of the coordinate. And when we multiply by the scale factor is when we get the actual physical size of the horizon. So light that starts at say time t equals 0, which we assume is the time at which the Big Bang occurred. In time t, so let's say it's the time in the present time, how far can that photon travel? That's what the horizon is, and that's the horizon. How far can you see is what a horizon describes. And for our universe, it can be calculated to be about 2 degrees in terms of angular size. So when we look at the sky, we can see objects. We can measure the size of objects in terms of angular size. We can, for example, if you look at the moon, it's around like an arc minute or so. But or if you look at the point sources like stars, those will be just a few arc seconds in size. So similarly, um, 2 degrees is what is the maximum distance that light can travel in, from when it started from the Big Bang till now. And this means that if you take the cosmic microwave background radiation that Srinidhi talked about a few minutes back, if you take 2 points in the CMB that's separated by larger than 2 degrees, that means those 2 points are outside of each other's horizon. Or in other words, they are causally disconnected, which means that it's not possible, given the current age of the universe, for photon to have traveled across that kind of distance. Otherwise, the light would have to it would have to travel faster than light to be able to reach those two separated points. Let's just, before this going ahead, I want to explain the CMB in a bit more detail. So the CMB is light that started its journey about when the universe was about 375,000 years old. That means 375,000 years after the Big Bang started. So it started out as visible light, but due to the expansion of the universe and due to the length it had to travel, it will stretch out or get redshifted to the microwave range. And what we now observe is the that radiation in microwave wavelength. And it's a perfect black body radiation, which means it perfectly matches, the predicted black body curve. And the measured temperature, this is the interesting part. The measured temperature is 2.725 Kelvin all over the CMB map. So that means if you take this map, it's actually a spherical map, but because we have to view it in 2D, it's been projected in this manner. And if you look at these, if you look at the different points in the CMB map, you'll see some blue points which indicates cooler regions, and some redder or orange regions which shows hotter regions. The thing is, if you take the blue region and the red region will only be like fractions of a fraction of a degree hotter than the cooler region. So yeah, the accuracy is up to 4 decimal places. That means if the blue region is about 2.725 degree Kelvin, the red region will be 2.725 1 or less degree Kelvin. So that's how that is how uniform it is. That kind of uniformity is not even seen, almost anywhere on Earth itself. So the challenge is that for something to reach that kind of uniformity, it has to have interacted with each other. It has to have attained thermal equilibrium by exchanging energy. So for example, if you take like a hot and a cold object, how does it reach thermal equilibrium? The molecules inside the hot object, if you mix them, the molecules inside the hot object and the molecules in the cold object like ice and tea, for example, these molecules will hit each other. It will transfer the hot object will transfer some of its energy to the cold object, and like that, it in some time it reaches thermal equilibrium. But as I explained earlier, uh, the CMB is separated by extremely, I mean, the different regions of the CMB is separated by extremely large distances. So how did it reach this kind of uniformity without having enough time to interact and reach thermal equilibrium? That's the challenge that's called the horizon problem. Um, so, and this is another illustration to explain the same thing. If you take a point in the CMB, and this is again like a spherical representation of the CMB, if you take this point in the CMB, the light from that, if you take, I'm talking about the little circles on the left and right. So if you take one of those circles, that represents a point from where light is coming out, or the radiation is coming out. And in 300,000 years, it would have only traveled that small, circle, or the radius of that circle. That's how much it is allowed to travel in 300,000 years. But there you can see that there's another point on the opposite side, right? I hope I'm being clear till now. Can someone confirm?
Yes, yes.
Okay. Yeah. So if you take the one on the opposite side, that also has a horizon. That circle is what you call a horizon, a maximum distance it can travel in 300,000 years. So how is it possible that these 2 points, which are separated by a distance much larger than its horizon, how is it that these two have reached thermal equilibrium? It's another a much more detailed explanation. Here again, it's like explaining the same problem again in a bit more detail. This is what we call a space-time diagram. So we have, you can ignore all of these coordinates and these units. Basically, the x-axis is space and the y-axis is time. And let's say we are at the point called here. That is, we are at a certain time in the present, and we are at a certain location in space. If we extrapolate back to this, the line that's called T last scatter. So that's where the last scatter means before the photons were actually kind of stuck inside this like hot plasma-like region. But once the universe started cooling down and structures started forming, the photons were allowed to start flowing freely, and that's when it started traveling towards us, and that's what we see as the microwave background. That's the blue line called last scatter, and that's where we see the CMB. Again, if you extrapolate backwards to t equals 0, you can see that there's to the time of Big Bang, you can see that there's no time for this reaction to connect to each other, or like there's no causal connection between these 2 points. Again, that's what we call the horizon problem. So these are just some calculations of how we can, the mathematical portion of how the horizon size, etc., are calculated. So if we want to calculate the physical size distance to the source of the CMB, we use the same integral that you saw in the beginning, but we take, we integrated from the time when the emissions were emitted to when it was observed, and that will be the distance to the CMB. And then if you take, coming to the next integral, next equation, if you take 2 opposite points in the sky, then it'll be simply 2 times. So like if you take a sphere and you're standing at the center and you look at one direction in the sky, and that distance is dCMB, and then the opposite side will also be dCMB. And the separation between those 2 points will be just 2 times that, basically the diameter of that sphere. So that's what's meant here. And the physical size of the horizon at the time that these CMB is emitted, that also we can calculate from by integrating it from 0, that is time of the Big Bang, till the TE, which is time of emission. That's 300,000 years later. And in cosmology, you must have seen that graph where you can see how A changes. And there's a time called matter-dominated universe where the amount of matter was much larger than the amount of radiation. And at that time, the scale factor was proportional to T raised to 2 by 3. That's the dependence on it of the scale factor on time. When we take that into account, the size of the horizon will be 3 ct, or that's how the size of the horizon changes with time, 3 ct. And so we want to compare this separation. It's basically the same thing that I said in the pictures, but in mathematical form. If you compare the D separation, that is the 2D CMD to the D horizon, it's found that it's much larger, like around 80 times or more, much larger than the horizon size. So again, it should not be possible, under the way we understand in the Big Bang model, it should not be possible for the light to have traveled that um, quickly and reach thermal equilibrium. So how does inflation solve this problem? In this space-time diagram, you can see that the 2 points that were causally disconnected at the Big Bang, we can extrapolate back to a time when they were indeed connected. So what inflation says is that there was a time right before Big Bang, which lasted from 10 raised to minus 36 to 10 raised to minus 32 seconds, like basically a fraction of a second, during which the universe underwent extremely rapid expansion. So, and at that time, all of these disconnected areas, what we see as being disconnected, were connected together. So if you go back here, all of these areas that were thought to be disconnected at the Big Bang were actually connected before the Big Bang, and the expansion is so rapid that these and also that it has had enough time to reach thermal equilibrium. So if you can see, there's a large difference between there's a large time gap between when inflation began and when inflation ends, and that is to signify that it has had enough time to reach thermal equilibrium. And so Big Bang began after these different parts of the universe had already reached thermal equilibrium, and it was sent out so fast and so rapidly that after the Big Bang, it stayed in thermal equilibrium. The thermal equilibrium was not disturbed by the expansion, and then it continued in the kind of expansion what that we see now. So these are again explaining it in the mathematical form. So during the period of inflation called inflationary epoch, the energy density of the universe was constant, and it remains unchanged by the expansion of space. So, like as I said, during that expansion period, the thermal equilibrium is not disturbed, um, and energy density is constant. And from the Friedman equations that Srinidhi explained earlier, we can solve it by a simple integration method like we take the square root and we separate the constants and the time dependent terms, and we can integrate and solve it to get the dependence of scale factor during the period of inflation. And we can see that it's an exponential term. So the scale factor increases exponentially during the inflationary period. So from this, we can calculate how much, or like the size of the horizon of the universe at the end of the inflationary period. So T begin is when the inflation began, and T end is when inflation ended. And we can see that it is again an exponential term, and it depends C e raised to h t n, where h is the Hubble's constant. And inflation theory. So in inflation theory, it predicts that inflation lasts from 10 raised to minus 36 to 10 raised to minus 32 seconds. And this corresponds to about 100 E foldings. That is, the expansion is basically E raised to 100 times. Okay. And when you apply this to the above equation, we get to be around 10 raised to 19 centimeter. So 10 raised to 19 centimeter is the size of the horizon at the end of the inflation. And the radius of the present observable universe, based on the equation we calculated earlier, that is 3ct, is 10 raised to 28 centimeter. And at the end of the inflationary epoch, or the period of inflation, scale factor was about 10 raised to 27 times. So when if you back calculate it, you'll get that at the end of the inflationary epoch, the size of the universe, physical size of the universe, was 10 centimeter, and this was well within the horizon calculated. It is much smaller than the horizon calculated. So that means so there we can see that that during, even though if we just look at the Big Bang period alone, these causally disconnected regions uh, different parts of the universe are causally disconnected. But when we look at the inflationary period, you can see that these regions were in fact very close to each other, and it would have had enough time to reach equilibrium. And then, of course, due to the rapid expansion, it was spread out to extremely large distances that we see today. And that's how inflation solves the horizon problem. Next, my friend Nagashree will explain the flatness problem and how inflation solves flatness problem. I'll stop sharing now.
I'm unable to share the screen.
You can share it now, yeah.
Oh, can you guys see my screen?
Yeah.
Yeah, okay. The first problem was horizon, and the second is the flatness problem. We all know the universe is flat. For the universe to be flat, the curvature the k, which is the curvature parameter, that should be equal to 0. So we all know from the experimental proofs that the omega is equal to 1. So omega is nothing but the ratio of the observed quantity to the critical density. So we have three cases. So when the omega is less than 1, it is called as the open universe. So that okay, I'll show this thing. Okay, so when omega is greater than 1, so if we just take some random 3 points in the universe and draw a triangle, the sum of those angles will be greater than 180. So if this was the case, then the whole universe would just we will call this as an open universe, so that everything would just fly off, and no galaxies or anything could have been formed. So so that is the positive curvature. So if omega is less than 1, which is the negative curvature, so the whole universe would lead to a big crunch. So it would recollapse itself. So we are living in the present situation universe where omega is exactly equal to 1. So the flatness problems the questions why exactly the critical density is close to 1. So even during the early stages of the universe, even if this omega even if this omega value, it would have been just greater than, a little more greater than 1, it would lead to open universe. And if it was less than 1, it would lead to the closed universe. So uh, yeah. So the question is how accurately this value was attained in the early universe, so that the universe is like flat now. So here looking at this Friedman equations, well, if we put k is equal to 0, we get this term. So if we solve this all these things, we will the right hand side, it is only constants. So we will know the energy density is like constant as stated earlier, and the scale factor A is increasing rapidly due to the inflation, and hence the omega term will decrease rapidly. So this shows the omega equals to 1, and hence the flat universe. Uh, Srinidhi, can you please take over?
Yeah, sure. I think you can stop sharing. Oh, okay. So that's it from our side, guys. So uh, so to draw some sort of conclusion from this, we can say that this combination of the inflation theory and the Big Bang theory, it 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 is the best explanation that we have for how the universe is in our present day. So I mean, we have different problems and concerns with the inflation theory as well, but I think the fact that it solves so many problems for us in such a simple way, it I think transcends all the other issues. So yeah, that's it from us, guys. Thank you for attending. Thank you, Sagar. We're done.
Thank you very much, guys. So, okay, Vikrant, if you're here, can you give your views and comments? How was the talk today?
Hey, can you hear me?
Yeah.
There might be a little lag because I'm slow. Please do excuse me. The talk was really good. I enjoyed it thoroughly, and I'm happy you guys chose this topic because inflation has always fascinated most of the science community, right? I mean, it's like something that is sort of derived from economic inflation, and then Alan Guth is like, hey, it's the same thing here, right? So I'm glad that you guys chose this topic, and I am looking forward to seeing your paper as well. The presentation was really good. I'm afraid I didn't see any references towards the end. It's always a good idea to show your references, even if it's a presentation. I don't know if you have it in your PPT and you just didn't show it, but for future references, it's always a good idea to also show your references at the end of the presentation. And
Yeah,
Srinidhi, I
so
think it's better if you share your presentation as Vikrant is explaining. I mean, presentation in the sense the paper.
oh, the paper is it? Okay.
Yeah.
Where am I supposed to share it?
I mean, share the screen and show
I
it
can
over
share
there.
the screen and then
Oh,
just
okay.
let us have a glimpse of how your paper looks.
Okay, sure, sure. Yeah. Just a second.
But yeah, like I was saying, even if you're doing a presentation, it's always a good idea to use citations and references inside your PPT as well, right? Because it's not limited to just doing it in your paper. It's always a good idea to also do it in your presentations. Even though you might distribute this PDF later on, where people can just search it by themselves, it's still a good practice to show them in your PPT at the end of your PPT. The last slide is usually references.
Okay, yeah.
Yeah, keep
Okay.
that for future. Fine,
Yeah,
right?
yeah, sure. Yeah. We'll do that.
Yeah.
Okay. Can I share the screen now?
Yeah. Go ahead, please.
Okay. Yeah. Okay. Is it visible now?
Yes.
Okay.
Nice. Okay. Mhm. Oh, there's no table of contents, is it?
No. We didn't actually put a table of contents here.
All right, no
It's
problem, no
just
problem.
yeah.
No problem at all. Cool. You can keep scrolling. It's going to take some time to actually read all of this. So
Okay,
I'll
okay,
just
yeah,
we'll just have a look at how your paper looks in general.
okay.
I'm pretty sure the content is well researched by you guys, and I'm hoping that all the citations are also proper.
Yes, yes. Yes, actually, there was some problem with the citations. So Sagar has
Mhm.
actually asked us to re-upload it once again. That we'll be doing once we're done with the with this
Right.
session now.
No problem.
Yeah,
No problem. That's okay. That's okay. As long
yeah.
as you figure out how to do it and it's there in your final submission, that's fine.
Okay, yeah,
Right? Because these papers might go up on our blog or some other nakshatra thing, and it's better if you have those references so that no one can sue you.
okay, okay, yeah.
Okay, Einstein's theory of gravity. Okay, all right, that looks good. Right, this part I think you covered in your presentation as well. So
Yes, yes, yeah. We covered it.
hmm. You can scroll a little faster if that's okay
Okay,
with you.
yeah, okay.
Okay, okay. CMBR. It looks pretty good to me. Hmm. Right. Okay.
Yeah, so the paper was actually structured differently. Our talk was actually structured in a different way. So
That's fine.
yes, we actually wanted to do it in the same order, but then there was some problem in deciding how to switch between ourselves. Like
Right.
we can't keep shifting, so we thought we'll
Right.
just change the order.
Oh, that's
Yeah,
okay. That's okay.
yeah.
I think you have a typo in section 5.1.
Uh,
Or is it
That's
inflaton? Sorry.
yeah,
yes, yes,
that's
yes. It is, it
Oh, yeah.
is. Yeah.
Then fine. Then fine. Oh, right. Huh. Okay. Yeah, I sort of missed that. It looks good to me so far. I think it's just the citations that is pending, right? Otherwise,
Yes, yes.
everything seems
Right,
fine
right.
to me.
Yeah, yeah. So
Awesome.
the citations we have to just change it a bit.
Right.
Yeah, so we'll be re-uploading it once we're done. Like after the
Sure.
session, we'll just do
Yeah,
it and
yeah, yeah. Take your
upload
time.
it.
Take your
Yeah,
time. It's fine. Just make sure that your final submission has proper citations and references in it. That's it.
sure, sure. Yeah.
Awesome. Hmm. One second. You go over to the conclusion.
Yeah.
Okay, I'll just because this sort of briefs entire thing that you've done. Right?
Right. Yeah.
Okay. Um, oh, yeah. Here's a small suggestion to this. Now, since your horizon problem and the flatness problems haven't actually been solved,
Hmm.
perhaps you can also add another line or maybe a paragraph, whatever it suits you, about what is open in whatever it is that you've studied so far. I mean, you have
Okay.
discussed
Fine.
the horizon and the flatness problem, but what next? Right?
Okay.
Conclusion. So it's some kind of an open-ended research where you have something else to take forward.
Okay.
It
Sure.
doesn't
Sure. Yeah.
and even if you guys do decide to take it forward in your bachelor's or in your master's or anything, then you can continue from here, right? So you have some starting point, and
Okay.
anyone who's reading this paper also realizes that, hey, I've read 17 pages so far, 16, 17 pages, but the problem still remains, right?
Hmm.
Your
Okay.
conclusion should sort of portray that the problem still remains. You've discussed it, you've given the mathematical reasoning, but the problem is still open. It hasn't been solved, right? So what is it that is left out? What is it that has to be done, and something like that, right? Maybe you can show that the problems are still open in a few lines.
Okay.
Yeah, but otherwise everything's great. It's awesome. Great
Okay.
job,
Thank
guys.
you.
All
Yeah.
three of
Thanks.
you.
thank you.
Great job. Sitara, if you're here and if you want to add something, please go ahead.
Yeah, hey, my audio is probably bad too. I have a lot of rains here, but I just want to congratulate you guys. Don't want to take too much of your time, but it's really awesome that you guys worked on this and put together something so comprehensive, I would say, in quite a short amount of time. And instead of just me commenting on it, I would love to hear from the team members. What were some of the highlights for you, and what was like a big takeaway, or something that surprised you perhaps in the journey? What did you learn especially? I would love to hear that from the people who worked on this.
Hey, okay. Yeah, so yeah, I think for all three of us, this is a completely new field. I mean, all three of us were actually interested in cosmology, but we haven't really done any work as such. So this project actually came at the right time for us, so that we could actually, invest some time in working on something that we like. So so coming to the topic, we actually debated a lot on what to take up, because a lot of
Yeah.
them involved yeah, I think we even spoke to you about taking up topics like Hubble tension and all of that. So all of that, yeah, the topics, some of the math formalisms were a bit too much for us to understand, back then, because we didn't really have any information or any knowledge about the subject. So then once we narrowed down on inflation theory, we decided that we're going to keep it as simple as possible, and not include a lot of math as such. But then as we kept on reading, it just it just blended in all of the technicalities and all of that, because so I remember the first time I actually watched Swagat's talk, the one that you sent me on inflationary cosmology, right?
Mhm.
So I think that was the starting point for me personally. I
Okay.
loved the talk. So and the fact that surprised me a lot was that that was the first time that I was actually hearing something about about cosmology as such. But it stayed with me. All of the concepts I could understand just by watching his talk. So that is where I felt that I can actually uh, give this sort of give even such a technical topic in such a simple way. So that is what motivated me to work on this more. So yeah, so again, thanks to you for sending that video, because that actually helped me a lot.
Wow, thank you. I will be sure to pass on that message to Swagat.
Yes, yes,
He'll be
definitely.
really happy. And yeah, I think he's someone who really believes in making concepts so simple and fundamental, but not to remove anything from it, So it is
Exactly,
important to
yeah.
maintain the integrity of the idea, but it's absolutely possible to present it in a nice way. And I think you guys have really proved that today. I
Thank you.
just logged in and I was listening to you guys. I expected something like super technical, and it was, but it was also surprisingly enjoyable to listen to. So you guys did a wonderful job, and it felt like you have digested a good number of topics properly, like kind of just played around with it till you've understood those things. So it's great. And I would be so happy if all the people who contributed to today's talk somehow ended up doing something in cosmology. It would be absolutely brilliant. It is a subject that's really close to my heart. So yeah, all the best to all of you. Julie, anybody else who wants to say anything, just in terms of, yeah.
Yeah, yeah. So thanks again, Sitara and Nakshatra and everyone else for the opportunity. And like Srinidhi said, we really surprised ourselves with how much we were actually able to learn about cosmology. And we didn't think it was possible in a few weeks' time. But yeah, especially personally myself as well, I'd heard cosmology talks before, so I had a very kind of surface level, like almost just I've heard these terms. I know a few of those things, but never really thought I would be able to like learn it deeply, but especially in such a short time. So this kind of this whole project like pushed me to do that, and we really surprised ourselves. And I think my favorite thing about the whole thing was as I learned about inflation and how Alan Guth kind of thought of this idea to explain this kind of anomaly or whatever. I found myself also thinking like a scientist. So when I was reading about his theory, his inflation, I was like, okay, it feels a bit far fetched. Is it even like, it didn't, it kind of, I felt myself becoming like a skeptic or like, thinking like an actual scientist, so where are you getting this idea from, or how are you going to make such assumptions that, the universe expanded so rapidly or things like that. And then of course, when you read more, you understand a little bit, but then you also understand, okay, there's a lot of gray area, there's still a lot of work to do. And I think that was my kind of my best, the best takeaway that I got from this whole experience. I kind of learned to think like a scientist, and even in topics as big as cosmology, which is like, yeah, which I thought would, which I've always been interested in, but never thought I would actually be able to, like think like a scientist or a cosmologist. So yeah, so for that I'm really grateful. And of course, I also found Swagat sir's talk to be extremely helpful. So yeah, so thanks for that as well. And yeah, thank you.
Hey, I'm so happy you guys went through with like Alan Guth. I mean, I don't know how many lectures you personally finished, but whatever it is you referred to, I think it's a great introduction to cosmology without the pressure of needing to know general relativity. And you can genuinely think as a fresh person into the subject. It genuinely makes you think about the big questions. And like you said, you can achieve a good amount of mathematical understanding with surprisingly less knowledge in relativity. So it's
Yeah,
great that you guys took that up. Yeah, so cool. And I'm guessing now, like Friedman's equations and like the concept of expansion rate and all that, it makes like a lot more sense to you, right? And I love those problems where there's the precision thing, or there is a horizon, there's a flatness problem, and how inflation seems to solve a lot of it, but it's still not straightforward. There is still so
yeah,
much
yeah,
left to do. So
Right.
yeah, if there's anything I learned from my very short understanding of cosmology, it is that the foundations are there but are not entirely strong, and they can break. And yeah, so I think you guys should also look at the mond and stuff like that, of which we will be talking about.
okay,
So anyway, I will just take this opportunity to conclude the talk. Give me a minute. Yeah. Okay, so I think Sagar will go ahead with an announcement, but I'll just be quick to do it. Basically, a lot of you have done this as part of the LaTeX program, but if you want to continue something, we've already offered you the opportunity of doing it for free as an open project, where we also offer mentorship. So I just wanted to say that from this week onwards on Discord, we are launching all the open projects and tribes officially. So you just watch out for those announcements. And some of you in this batch particularly, we would love to talk to, and get to know you guys a little bit more. So if you can sustain your interest for 2-3 weeks more, we would really be happy to have some more informal conversations, so that we can dive into topics in a more exciting way and question some of the stuff, right? So that's basically the point. Like, how much can we question? How much can we kind of deconstruct particular concepts that we think we know already? So yeah, let me just hand it over, but I'll just go through the list, right? So there is quantum mechanics tribe, and of course, let me first of all say there are two things. There are tribes and there are open projects. A tribe is a lot like a focus study group, or a club. So we have, in focus study groups, you basically explore a topic in your own way, and you have a team to do it with. For example, quantum mechanics, and every week we'll be exploring a different topic. So that's something fun, but it's also extremely informative if you do it properly. An open project is very similar to what you guys did, with a minimum 30-day involvement requirement from the side of the participant. But you're expected to work on something and produce at least a concept paper. A concept paper is something like what your team presented today, but it's not as, it doesn't have to be as comprehensive. It can be a bit shorter. Um, but the idea behind the open project is that you also develop skills along the way, right? Not just the theory, but the skills to play with the mathematical equations or propose your own idea. So open projects are a place where you can be bold with your proposed ideas or your conjectures or hypotheses. So we are really going to explore what happens if young people like us come and try to put out scientific hypotheses, and we really try to prove or disprove them, right? What can we achieve? So yeah, that's kind of what we choose. It also depends on which one you want to be a part of. So I'm just going to go through the list. Quantum mechanics tribe is open, and that is going to be along with Sagar, who will be conducting most of it. Then there is coding and simulations, which is a very interesting group if you're interested in physical simulations. Basically, how do you mimic nature with the help of programming? Maybe it's a leaf in the wind, falling down. What are the forces that are subjected on this particular leaf? Um, so yeah, okay, he's showing that. So yeah, the programming that you see there, that's basically the simulation group. It is an open project. Neuroscience, as you know, every Saturday we will be meeting with a researcher from TIFR and talking about different things like evolutionary biology, adaptive behavior, behavioral psychology, and like last time, a little bit of psychedelics and biochemistry. So we hope to cover 2-3 big concepts at least in this series. And that's a tribe. And complex systems is another tribe that will be led by Sejal from NIT. I don't know if she's here. And we will be talking about chaos theory, nonlinear dynamics, genetic algorithms, game theory, and stuff like that. And we will try to be as multidisciplinary as possible with complex systems. We'll try to apply what we learn in economics or physics, biological, systems and things like that. Cosmology is today what you guys presented. We want to make that experience of learning the fundamentals of cosmology open to everyone. So that is just something that we hope the students will do, right? We want them to start with Friedman's equations and work their way up in the understanding of introductory cosmology. So hopefully what you guys have done today will serve as a skeletal structure for many incoming students who wish to learn the same. So congratulations on that. I honestly think it should behave as a blueprint for people going ahead. So if any one of the presenters today would like to also involve or take a little bit of leadership, you are absolutely welcome to join our academic team. Then we have biochemistry. I think Anandu, I'm not sure if he's here, but he's going to be taking that project forward. And finally, the dark matter project will dive a little bit deeper into potential candidates of dark matter this time, probably with a focus on WIMPs and also much lighter particles. And we also hope to focus on the process of detecting it and not just study. There are so many detectors that have come up, but we don't understand them properly. And maybe the reason we've not found anything so far is a deep underlying technical issue. So we want to also give some focus to the detection techniques. Okay. So that's it. Everything is going to happen. All of these free programs are on Discord. So just make sure you join in case you're not there already. But you guys already know about this community. So we are saying this to you because we want you to take more than just an participant position. We want you guys to take leadership if possible for some of these, and if you want to propose new clubs or whatever it is, you can do so. So we just want to welcome you into the inner circle of Nakshatra if you are willing to join, because our doors are open and we would just love to see what's possible. I mean, Sagar was exactly like you guys like a year ago, and he's taken so much leadership and taught and mentored so many kids. Vikrant is still doing his masters, but he's just taught so many topics now, and he basically has expertise of being able to convey topics clearly. And that's such a cool skill to have at such a young age. So yeah, you never know what's going to come out of taking leadership. So that's what we encourage you to do so. He has sent the registration form if you want to be a part of either a tribe or an open project. You simply have to fill that form and also be present on Discord, and therefore we'll be able to acknowledge your work by the end of it that way. Okay. So with that, I'll close. Again, congrats, guys. I'm so proud that you took the effort and the deliberate, um, dedication and decision to make this happen. So great paper. I think you guys can go ahead and do something more technical, honestly. So if that's on your mind, please DM me. We can work something out. Okay. Cool. Thank you.
Sure, thank you. Thanks a lot.
Guys, if you're not in our community now, I've shared the link for Discord and Nakshatra Discussions Telegram group. Please join them. And all our events will be happening in Discord, the mentioned by Sitara. Okay, guys.
Okay.